Welcome back to part 2 of lecture 5 for MAE170. So in the second part of the lecture, which is going to be pretty quick, I just want to show you what happens when you take an open loop second order system and you close the loop. So in other words, we want to see how the poles of the system shift, if they move or if they're the same. So remember, we started from the open loop. So we only have our system as G of S with an input and an output. Now what we're going to do, we're going to close the loop. That is, we're going to add a feedback system. And as I said last week, we're always going to consider unity feedback system. That is, we don't really have a transfer function for the sensor. We can also take the overall closed system and indicate its transfer function as T of S. So in other words, we can write the closed loop system as the input that is fed into this closed loop system, and then we have the output. So now T of S represents the transfer function for the closed loop system. We've already seen that the transfer function for this closed loop system is given by the open loop transfer function G of S over 1 plus G of S. So considering G of S, as we saw before, as omega n squared over S squared plus 2 omega n zeta S plus omega n squared, we can find that T of S is right. So this ends up being omega n squared over S squared plus 2 zeta omega n S plus 2 omega n squared. Now notice something very important, that we started from a second order system. Once we close the loop using a unity feedback closed control system, we still end up with a second order system because the denominator is still a second degree polynomial. Now, if you compare the denominator of G of S with the denominator of T of S, you'll see that there is something slightly different. And in fact, we have that this term, the constant term of the polynomial at the denominator, goes from omega n squared to 2 omega n squared. So obviously, when we want to find the poles of the closed loop system, that is, we want to find the solutions of the characteristic equation associated with it. This is the characteristic equation, or we can write it as delta CL for closed loop of 0. Well, we're going to have different poles than the poles of G of S. So in order to use different symbols, let's rewrite the characteristic equations. Now we're going to use, instead of zeta, we'll use the symbol which is known as psi. So zeta and psi. And then instead of small omega n, we're going to use capital omega n. So that we still have the same structure for the second order system, but with different natural frequency and with different damping ratio. So now the natural frequency for the closed loop is this capital omega n, and the closed loop damping ratio is psi instead of zeta. Now let's find the values for this new natural frequency and this new damping ratio. So what we are going to do is we're going to equate coefficients, of this equation and this equation because they are the same. So starting with the constant term, we have that the closed loop natural frequency is equal to, or squared, is equal to 2 times the open loop natural frequency squared, or the closed loop natural frequency is equal to square root of 2 times the open loop natural frequency. So we have that the natural frequency, once you close the loop, increases by a factor of square root of 2. What about the other coefficient, the coefficient of the S term? Well, we're going to have that zeta small omega n is equal to psi capital omega n. We also have a factor of 2, but that cancels out. So psi is equal to zeta times small omega n over capital omega n. So substituting what we've just found, we have that psi is equal to zeta divided by square root of 2. So the natural frequency increases whilst the damping ratio decreases. That's exactly what it's written here. We have the natural frequency for a closed loop system, second order system increases and the damping ratio decreases. Of course, if we already start with a damping ratio that is equal to 0, then it'll just remain equal to 0. So the closed loop poles, if the damping ratio psi is between 0 and 1, can be written as minus psi capital omega n minus and plus I capital omega n. We're using the same fashion, same kind of expression that we found earlier, just with the 2 new symbols for natural frequency and damping ratio. All right, so in this first box, this is P1 and P2 for psi that is all the way from 0 to 1 included. And if instead psi is greater than 1, then P1 and P2 are going to be simple real numbers. And once again, the expressions are very similar to what we found in part 1 of the lecture, with just the 2 new symbols. All right, so let's first analyze the first case, and then we'll see the second case. So if we start with the open loop poles that are complex conjugate, so let's say that they lie on the semicircle of radius, as we saw, small omega n, we can notice that we found that zeta small omega n is equal to psi capital omega n. But remember that zeta omega n was the real part of the old poles. And this tells us that the real part of the open loop poles is equal to the real part of the closed loop poles. So what happens is that when we close the loop, the poles move on a straight line. And in particular, they move away from the real line. Why do they move away from the real line? It's pretty simple to understand why this is the case. Remember that the new natural frequency, omega n, is equal to square root of 2 times the old one. But the natural frequency, as we saw in part 1, is the distance between the pole and the origin. So the distance has increased to square root of 2 times the old distance. So obviously we can only go away from the real line. So if we consider once again the open loop poles with those green crosses, once we close the loop, then we have this magenta purple crosses, and they are more far away, further away from the real line. Now let's consider the second case in which the open loop poles are real numbers. So we start with this expression and we end up with this expression. And here I'm just considering P1. Of course, the same can be said for P2. So let me just visualize P1 on the complex plane. So we're starting from a real number. Now we want to know, if we close the loop, where does it move? Where does P1 move? Is it still real? Does it move away from the real line? Does it become a complex number? Let's see. Well, we already know that it remains a real number because we don't have any imaginary part. So we have two options. We can move to the right, that is to lower number in magnitude, lower real numbers in magnitude, or to the left with greater magnitude for the real part of the pole. So where are we going to move? Well, we have to compare P1 for the open loop case with P1 for the closed loop case. So for instance, I'm asking, is P1 for the open loop case less than P1 for the closed loop? Let's take a look. So this is the open loop pole. So is this less than the closed loop one? Well, first of all, we have that this part and this part are the same because of this equation. So we can cancel them out. We also know that capital omega n is equal to square root of 2 small omega n. And then we know that psi squared is equal to zeta squared over 2. So we can get rid of this and this. We change signs on both sides, so we have to flip the inequality. And so we're left with this inequality. Is it true? Well, since in this case zeta is greater than 1, obviously zeta squared minus 1 is greater than zeta squared minus 2. So our first assumption was valid. So in this case, it means that closing the loop, we have a greater value for the pole. So we are closer to the 0. So in other words, we move towards the right, or P1 moves towards the right. The same thing can be said for P2. Let's say that if P2 was over here, then closing the loop, we would just move to the left. All right, so that's something that I wanted to tell you guys, that if you start with an open loop second order system and you just simply close the loop, again, without introducing any controller or anything, what we've just done is taking G of S, which was the transfer function of the open loop system, we just close it. Then the poles, if they are, or if they were complex conjugate, remain complex conjugate. They just move away from the real axis. And instead, if they were real, they just move towards each other. What can happen is that if we were close enough to this dashed line, you could have that the poles could move on to the dashed line, and from real numbers, they can become complex conjugate. All right, so this is really all for today, and I'll see you next time. Take care.